Poe from Wilmington Grammar School for Boys, and today we're going to be looking at discrete distributions. So what do I mean by discrete distributions? Well, I've said this before, but just to remind you, when we're talking about something that's discrete, and that is a terrible size, let's make it a bit smaller. So when we're talking about stuff that's discrete, we're talking about data where the data comes in packets. Okay, now the packets don't overlap, and the packets may have an edge that they share in common, but for example, if I went to a shoe shop and I had shoes that were sold in sizes of 2s, 3s, 4s, 5s and so on, or 2.5s. I mean, technically you could quantize it with halves, so 2.5 would be there, 3.5 would be there. That's okay. The point is these come in packets, in pre-arranged steps, if you like. They don't necessarily have to be whole numbers, but it just has to be one or the other. So for example, if there's discrete data where your data can only be, say, steps of 0.1, so say it's all the values from 0 to 5 going up in 0.1s, you can't have a value of 5.23 because that's clearly, well, it's going to have to be a choice of whether it's 5.2 or 5.3. It depends on the question. So hopefully we should have an idea of what we mean by discrete to start off with. Now, distribution. Well, a distribution is just another way of explaining how data could be picked or how it's arranged. And what we're going to mainly look at today is what's called discrete random variables. And the way to think about this is variables, we know what they are already, they're things that can vary. Random, there's an element of randomness, luck, probability, that kind of thing. And discrete, because these variables take discrete values. So we're going to be looking at discrete random variables to begin with, and I'm going to take a really easy example that hopefully you guys have all seen before. When I say you guys, I mean you guys and girls, obviously, you people. So let's visualize something hopefully we've all seen before and played with. Now, it wouldn't be too much to suppose that we've seen one of these before. And let's assume that this is a fair 6-sided dice with numbers 1 to 6. And we throw the dice. It's fair in the sense that they're equal probabilities of landing on a particular side with side up. And we read whatever the value is on the top, like so. Now you should have a fairly good understanding of how dice work and what could potentially happen. But what we're going to be doing is we're going to be saying, okay, let X be the score. Okay, so let's think very carefully what's going to happen when we roll a dice. Well, we could either get a score of 1, 2, 3, 4, 5, or 6. And now I'm going to create a table like so. And this row is going to be the probability that my discrete random variable capital X equals a particular score little x. So that's a clear distinction. So here we're letting our discrete random variable X be the dice roll, and little x is the score value. Now that's worth noting, they are subtly different. I doubt you'd be tested on something like that, but it's just good to know. So because this is a fair dice and there's six outcomes, then clearly the probability of landing on each of these faces is going to be a 1 in 6 chance. Now you probably had an idea of something like that in your head, i.e. each of the faces are equally likely to appear. You might also have the idea that you need to roll a dice on average 6 times in order to get 1/6 maybe on average. there's various different concepts of how dice work there in your head, and what I'm going to do is talk about some common attributes of discrete random variables and how they work. The first thing I want to talk about is this thing called E of capital X. And what E of X is, what this is the mean. Or we use E because we say that's the expectation. Okay, the expectation of X is another way of saying the mean. Okay, so another way is you say, well, what would we expect on average the output to be? If I was to perform this probability experiment, or I was to, try out this discrete random variable, what would I expect to get? And it's very simple. What it would be is it would be the product. Okay, let's write this down. Let's see, it would be the sum from I going to 1 up to n. So for all of the distribution, for all of the values, and this is the expectation of X, where X has n outcomes. Then it would be xi, the score, times by the probability that the variable equals xi. Okay. Now you're probably thinking, what does that mean? And it's very simple. If I was to calculate the expected value of x, then what it's saying is for every score value, xi, so 1, 2, 3, 4, 5, 6, you need to multiply it by its corresponding probability, which is 1/6 for all of them, and then you need to sum them all up. So let's do that. So in this example, we've got 1 times 1/6, which is 1/6, plus 2 times 1/6, which is 2/6, plus 3 times 1/6, which is 3/6, plus 4 times 1/6, which is 4/6, 5 times 1/6, which is 5/6, and 6 times 1/6, which is 6/6. If I add these all together, I believe I'll get 21 over 6, which I also believe is 7 over 2. So the average score would be 3.5. Now that should make sense for a couple of reasons. One, 3.5 is dead in the middle of the scores. The other thing is, because all the probabilities are the same, this is what's called a uniform distribution, i.e. all of the probabilities are uniformly distributed. They are distributed uniformly. When something's uniformly, they all do and act the same. It's a bit like when you're at school, you're all made to wear a uniform, you're all supposed to look the same, you're all supposed to dress the same. When something's uniform, they happen all like each other. So it doesn't bear a particular surprise that the mean, the average, should also be the median position of the scores, dead in the middle, because they're uniformly distributed. If the probabilities were higher, pardon me, at one end, then you'd expect the mean to be, you would expect the mean to be shifted over a little bit, but it's not. Okay, second point I'd like to make is the sum of the probabilities must equal to 1. So maybe that's not entirely obvious, it should be. So the sum of all the probabilities of x equaling little xi, where I goes from 1 up to n, that should equal 1. That's a little factoid you should know, and that should make sense as well, i.e. the sum of the probability of every single outcome should equal 1. It's like the sum of the sample space. Now, if you remember when we were talking about measures of location, measures of spread, central tendency, all that stuff, there's one more statistic that we're interested in, and that's called the standard deviation, sigma. So the standard deviation, which is just literally saying standard, which is another way of saying average, normal, and deviation, how things deviate, the distance. It's literally the average distance away from the mean you'd expect each point to be. Now, when we deal with discrete random variables, we don't really talk about it like that. We work with something called the variance. So when I'm talking about the var of x, I'm talking about the standard deviation of x squared. So if I really wanted to work out the standard deviation, I would just square root what the variance is. Now, here's the formula for it. The variance of x is the expectation of x squared minus the expectation of x all squared. Okay. Now, if you're wondering where that comes from, I explained in another video, right, how to work out the standard deviation, and if you want to, can you prove it given what we've known so far? This should look very familiar to you in actual fact, because this should scream bells of x squared, the sum of x squared over n minus the sum of x over n all squared kind of thing. And if you square root that, that was the standard deviation. And in actual fact, I've kind of done it for you, because if I square both sides, I get this, and sigma squared is the variance, and yeah, this is clearly the average of x squared, and this is clearly the expectation all squared. So that shouldn't come too much of a surprise, really, if you just think about it. And you know, there's a couple of other little minor points with discrete random variables. Sometimes you might run into something called a cumulative distribution, and that's usually with f. So, for example, if I wanted in my example I'm dealing with now, if I wanted, say, f of 3, that's the same as the probability of x being less than or equal to 3, which is just going to be the sum of x equals to 1 plus the sum of x equals to 2 plus the sum of x equals to 3. You literally just add them all up, and that looks like it's going to be a half. You just have to be very careful when you're constructing tables. But essentially, discrete random variables, that's pretty much it. If you know how to work out the expectation, you know how to work out the variance, you understand the sum of the probability rows equal to 1, you know about the cumulative distribution. I think one other point is coding, for example. I think that's probably the last point, actually, thinking about it. Let's get rid of this. Coding. Let's say I want to perform a linear transformation such that y equals, let's say, ax plus b. Okay, let's suppose that I don't like x for some reason and I want to change it into something else. Then the following happens. If I want to work out the expectation of y, which is the same as the expectation of ax plus b, then all I need to do is take the expectation of x, times it by a, and add b. And I'm hoping that should make sense. And the reason for that is because if I have a data set, here's my data set, like that, look what happens. If I perform this transformation y equals ax plus b, the b part is just going to horizontally move it around. So you'd expect the average, well, let's make the average have a circle around it, so that's x bar, or the expectation. You'd expect that to move around as you'd expect. Now when I multiply by a, That's the same as this expanding. And again, the average would behave just like you'd expect. That's not a problem. However, things get a little bit trickier when it comes to the variance of y, because that is going to be the variance of ax plus b, and this is just going to be a squared of the variance of x. Okay, these two formula are going to be really useful. Well, let's think, why is it that when you do stuff, when you code it linearly, the variance gets times by a squared? Well, remember, the variance is the square of the average distance. So if I double all the distances between the points by this factor of, well, if a is 2, for example, if I magnitude this by a, then the standard deviation, the average distance, is going to get a times bigger. And so the standard deviation squared is going to be a squared times the standard deviation squared. So the variance is going to get a squared bigger. The plus b term is going to be irrelevant, because as long as I've made this bigger, it doesn't matter where I slide this around, the average distance is going to be the same still. Shifting this along left and right is not going to change the average distance between the points. It's that a squared bit that's important. So yeah, those are the key concepts for this. It's pretty much all you need to know in actual fact for discrete random variables at this point. Let's just go through a couple of examples. So, pause the video, give a second for yourself to try this one. Okay, let's go. So, the random variable x has probability function that the probability that x equals little x is kx when x is 1, 2, 3, and it's k times x plus 1 when x is 4 or 5. Okay, let's just get this into a table. So we've got the score of x, and it can be 1, 2, 3, 4, or 5, and the probability that x equals little x over here, well, it's kx when x is 1, 2, 3, so it's going to be k times 1, k times 2, k times 3 for the first three, and then it's k of x plus 1 for the next couple. So 4 plus 1 is 5, so that'll be 5k, and 5 plus 1 is 6, so that's 6k. Okay, so here is my discrete random variable table. I've just got it into a form that I've shown you before. I mean, don't be intimidated by this stuff. Just read it and do what it says. Find the value of k. Well, what do I know? I know that the sum of all of these probabilities must equal to 1. So 1 plus 2 is 3, plus 3 is 6, plus 5 is 11, plus 6 is 17k. This must equal to 1, so k equals 1 over 17. I think that's right. 6 plus another 6 is 12, plus 5 is 17, yeah, cool. Okay, find the exact value of the expectation of x. Okay, well, the expectation of x is just going to be the sum of 1 times k plus 2 times 2k plus 3 times 3k plus 4 times 5k plus 5 times 6. So how many k's do we have? So this is for part A. Part B, how many k's do we have? We've got k lots of 1k plus 2 times 2, which is 4, plus 3 times 2, which is 9, plus 4 times 5, which is 20, plus 5 times 6, which is 30. So 1 and 9 there is 10, plus another 20 is 30, plus another 30 is 60, plus the 4 is 64k. So 64k is going to become 64 over 17. And as an exact answer, I don't think that simplifies down. 17 is a prime. Nope, we'll leave it as that. 64 over 17. If you're interested, that's 3 and 3/17. So the average is going to be somewhere between the 3 and the 4. Okay, show that the three significant figures, the variance of x is 1.47. Okay, so for part C, the variance of x is going to be the expectation of x squared minus the expectation of x all squared. So the expectation of x squared, That means we square the scores first and then we times them in. So 1 squared times k is 1, so we've got k lots of 1, plus 2 squared, which is 4, times by the other 2, which is 8, plus 3 squared, which is 9, times 3 is 27, plus 4 squared is 16, times 5, I believe, is 80, plus 5 squared, which is 25, times by 6, which is 150. So in total, I've got 1 plus 8 plus 27 plus 80 plus 150, and then I divide that by 17, I will get 266 over 17, and then I have to subtract the expectation of x, which is 64 over 17 squared. So that number minus fraction 64 over 17, and square that. So it is 1.4740484443 and so on. And if I take a look at the second decimal place, yes, it does equal 1.47 to 3 sig figs. So yes, that is true. Okay, part D. Find to one decimal place the variance of 4 minus 3x. Okay, so the variance of minus 3x plus 4 is just what I was talking about up here when you do some kind of linear transformation. So this minus 3 is going to be taken out and squared. So this is the same as minus 3 squared, which is 9. Lots of the variance of x, and the 4 does nothing. So all I have to do is 9 times that answer. So if I times it by 9, I will get 13.3 to 3SF if I carry over the answer from before. So yeah, to one decimal place, 13.3. Yeah, cool. That was it. All right, next question. If you want to pause the video, give it a go yourself. Okay, so the random variable x has probability distribution blah 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 blah. Given that e of x equals 4.5, write down the two equations involving p and q. Right, first of all, the sum of the probabilities rows equals to 1. So I know that 0.2 plus 0.2 plus 0.15. So I know that 0.55, which is that, that and that, plus p plus q must equal to 1. So that means 1 minus 0.55, which is 0.45, means that p plus q equals 0.45. So when it says write down two equations involving p and q, there's my first one. The second one is probably when I'm going to involve this expectation of x. So let's deal with that. The expectation of x, which is 4.5, equals 1 times 0.2, which is 0.2, plus 3 times p, which is 3p, plus 5 times 0.2, which is 1, plus 7 times q, which is 7q, plus 9 times 0.15, which I believe is 1.35. If I tidy all this up, 4.5 minus the 1.35, so that will go, and then minus the 1, so that one goes, and then minus 0.2, so this one goes, will mean that 3p plus 7q equals to 1.95. And now that's the second equation in terms of p and q, and I can probably just solve now. So what am I going to do? Well, I'm probably going to eliminate for p first. So if I multiply equation 1 by 3, I will get 3p plus 3q equals to 3 lots of 0.45, which is 1.35. And if I take that away from 3p plus 7q equals to 1.95, I will get 4q there, and then this is 0.6, I believe. Yep, so then q equals 0.15. And then I can substitute that back into maybe equation 1 to get p must be 0.3. So that wasn't too bad at all. Next question. Find the probability that p is greater than 4 but less than or equal to 7. So what values are greater than 4 but less than or equal to 7? Well, it's just the 5 and 7, isn't it? So it's going to be 0.2 whatever Q is, plus whatever Q is. Or 0.2 plus 0.15 is just going to be 0.35. So that was a fairly nice self-contained question. Okay, given that e of x squared is 27.4, find the variance of x. Well, that's just going to be e of x squared, which is 27.4, minus e of x, which is 4.5, squared. No problem at all. 27.4 minus 4.5 squared. And that is 7.15. Okay, find the expectation of 19 minus 4x. Well, this is what you'd expect it to be. This would be 19 minus 4 lots of the expectation of x. So this will be 19 minus 4 lots of e of x, which is 4.5. So that is just equal to 1. And the variance of that is just going to be, well, the 19 is not going to contribute. The minus 4 comes out and squares it, so that's 16 lots of the variance of x. So all I need to do is times this number by 16 to get 7.15 times by 16, which will give me 114.4. There you go. Not too bad at all. Okay. Right, next up, I want to talk about the binomial distribution. Okay, what is a binomial distribution? Well, two things. A binomial, right, literally is a two-numbered thing or a two-termed thing. So I want a distribution that has two terms. And the way I'm going to describe that is it's discrete, so it can have two outcomes, and you either win or succeed, or you lose and fail. There's no in between. Okay. You can't have a draw. There has to be two distinct outcomes. Yeah, that's it. And usually the probability of winning we denote as P, and the probability of losing is just 1 minus P. So that's consistent with the sum of probabilities equaling to 1. A few other things. Well, they have to be, the trials of this distribution have to be statistically independent, i.e. They kind of reset after every trial. So if I win one time, that's not going to affect the probability of me winning the next time. There's no kind of bias in that sense. The other thing is there must be a finite, fixed amount of trials. Okay, that's also important. There also must be a fixed probability P, but that's kind of loosely in here as well. That probability P does not change. It's agreed beforehand, all that kind of stuff. I'm just trying to think, does anything else you need to know? So, win, succeed, yeah, so there's two outcomes, they're discrete. The trials are statistically independent. The amount of trials is fixed and finite, and the probability itself is fixed. Yeah. Now, this is quite all-encompassing because there are other distributions as well that behave similar like this, and they are called Bernoulli trials. And in fact, the binomial distribution is one of them. There's a few other examples of Bernoulli trials. We're going to be covering stuff like the negative binomial distribution and the geometric distribution, just to name a few. But yeah, let's look into the mechanics of how this thing works. So let's take a really easy example. Let's suppose okay. Here's an example. So, e.g., we've got a coin. It's a fair coin, and we're going to flip it 10 times. Okay. Could this be considered to be a binomial distribution? Well, yes, it can, because there is a win and a lose. For example, I might declare heads as winning, or the success. The trials are statistically independent. Or if I flip the coin once and I get a heads, if I then reset that and flip the coin again, then the probabilities are reset. It's not like if I flip ahead once, it's more likely to flip ahead the next time. Is there a finite fixed amount of trials? Yes, I've chosen 10, so that's fine. Is there a fixed probability value? Yes, the probability value here is just 0.5 or a half. If this is a fair coin, then it's a 50% chance of landing on heads, 50% chance of landing on tails. We're going to ignore any silliness. For example, we flip the coin and it lands on the floor such that it's on its side and you can't tell whether it's heads or tails. We're going to ignore all stuff like that. So, you know, no being too smart for your own good. Yeah, so how do we express this? Well, the way we do that is we let our distribution x, and by the way, we defined capital X last time, so let's use a different letter. Doesn't matter. And they're usually capital letters. Okay, when we're talking about distributions, we usually use capitals for distributions. You don't have to, but generally speaking, that's kind of like that's the thing. So what we do is we say y is distributed, so that's what that tilde means. So this means distributed by, and if I wanted to use the binomial expansion, I'd use a b, and then there's two parameters that define the binomial expansion. One of them is the n value, which in this case is 10, and the other value is the p value, which in this case is 0.5. So again, really important. This is the n, or number of trials, and this is the p value, and this is the probability of success. Okay. Now, let's do a couple of twiddles with that and see what we can come up with. Right, first of all, let's deal with a statistic we wanted last time. What is the expectation of x in this case? Well, it turns out to be n times by p. And hopefully you can see that 10 times 0.5 here would give 5. And we'd expect out of 10 coin flips that the probability of getting heads would be 5 times out of 10. That, to me, that just makes more sense intuitively. What doesn't make sense as so much is the variance of x is n times by p times by 1 minus p. So this is the number of trials times by the probability of success times by the probability of failure. So this is trials times by success times by failure. Okay, now you'll be given these formulas in a formula booklet, but to be honest, you do it a couple of times, you just kind of memorize them. And these are kind of the key statistics for any distribution, really. When you get a distribution, you want to know the average, the expectation, and you want to know the variance. If you know those two objects about a distribution, then you pretty much understand the shape of it. There's a couple of other things. For example, the cumulative distribution here. So, same deal. If I want the probability that x is less than or equal to, let's say, n, then this is just going to be the sum from 0, because we could have 0 successes, right, up to n, and this will be all the probabilities that x equals to xi, like that. Okay, so just be very careful with the probability distribution. If say for example I wanted the probability that x was less than or equal to 3, then that would be the probability x equals to 0 plus the probability x equals to 1 plus the probability x equals to 2 plus the probability that x equals to 3. Okay, so just bear in mind with the cumulative distribution you have to start at 0, because we could flip, in our example, we could have flipped the coin 10 times, and there is a finite possibility that we could get 0 heads. It doesn't just start at 1, it starts at 0. So if we want to include all the times up to and including, so this would be, for the example of at most 3 heads. Now, if I wanted to do it the other way around, let's say I wanted the probability that x was greater than or equal to 3, then this is pretty easy to do. All I do is 1 minus the probability x is less than 3, which is exactly the same as 1 minus the probability x is less than or equal to 2. Okay, you just play around with it. So this is in the case of at least values. And why is that? Well, let's suppose in our example we had, what was it, 10 results? Oh, I had to make it difficult for myself. So let's suppose I'm going to represent this pictorially, where the y-axis is the probabilities and the x-axis is the scores. So I've got, let's say that's 0, that's 1, that's 2, 3, 4, 5, 6, 7, 8, 9, 10. Run out of space. Okay. So where are we? So I think the 5, 1, 2, 3, 4. Yeah, the 5 is going to be the tallest. And it's going to be symmetric about the 5. Something like this, maybe. They should all be equal width, but I've drawn this a bit sillily. Okay. So, suppose I wanted probability that x is greater than or equal to 3. So that's this bar, 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 this bar. Well, since the areas under these bars all equal to 1, then surely I can just find the areas of the first 3 bars, 0, 1 to 2, like that. So this is the probability x is less than or equal to 2, sorry. So I'm hoping you can see how that holds. Because what we're saying is that, you know, the probabilities at each of the scores is going to be a certain value, and the sum of those probabilities is equal to 1. So if I want all the probabilities above a certain value, then I could just do 1 minus all the probabilities below that particular value. But you just have to be very careful because this is a discrete case, so it's not quite as simple as doing 1 minus the probability x is less than or equal to 3. You just have to be really careful there. Okay, now, crunch time. You're probably thinking, okay, what is the probability of getting x being equal to 5? i.e. what's the height of this bar, what's the height of the 4 bar, what's the height of the 3 bar, and so on and so on. Right, okay, this is the meaty bit. So, the probability that x equals to x with the binomial cases, well, let's think about it. I want x amount of successes. So it would be p to the power of x, because I've got x amount of successes of p, and then the amount of failures I'm going to have is going to be n minus x, isn't it? Because if I've got 10 trials, let's say n was 10 and the amount of successes I want was 3. So then in this case it would be p to the 3 because I've got 3 successes, and then it would be 1 minus p, which is the failures, to the power 7. And now here's the really interesting thing. Hopefully you can see the parallels between this and the binomial distribution, is how could these be ordered? For example, we might have heads, 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 and then 7 tails. Or we might have heads, heads, and then a tails, and then a heads, and then the rest tails. The point is we've got 10 objects, and we want to choose the position of 3 of the heads. Right? There's 10 choose 3 possibilities. So what's going to happen here is we're going to have n objects choose x, like so. And now this formula tells us the probability of x equaling to x, and the probability that x is less than or equal to x, I'm hoping you can see a similar argument, is going to be the sum from I equals 0 up to little x of pi times by 1 minus p to the n minus I. Now this right? Really important. Whoops. And this is n choose I, just slotted in there. Now, in actual fact, we've now got all of the bits we need for the binomial distribution. So let's answer that question now. What's the probability of getting 5 heads? Well, it was going to be 10, so the probability we were going to get 5 heads. It would have been 10 choose 5, because out of 10 flips we want 5 to be successes, and then 0.5 to the power of 5, because we wanted the 5 heads, and then 1 minus the probability of success, which is 1 minus 0.5 to the 5 failures. So, quick calculator time. Let's have the run matrix. Let's do a bit of math. No. Option. Stats. No. Probabilities. Yep, there you go. So I'm going to need 10 choose 5. So this is going to be 252 times by 0.5 to the 5 times by 1 minus 0.5, which is still 0.5 to the 5. So if I times that answer by 0.5 to the power 5, and then again, I will get that probability is 0.246 to 3 decimal places. And you're probably thinking, okay, so it's about a 24% chance, just under a quarter. So just under a quarter of a time, you're going to get 5 heads. Okay, let's take an easier example. Okay, let's say I flip the coin twice. So 2 flips. Let's say 2 flips. Okay, so let's think about it. They're either going to be heads heads, or heads tails, or tails heads, or tails tails. So if I want the probability here, if let's call this Z, is binomially distributed with 2 coin flips, and the probability of success is 0.5, then clearly the probability that Z equals to 1, i.e. I have 1 heads, well, let's think about it. The probability of heads times a heads here would just be a half times a half, which is a quarter. Probability of heads times tails would be a half times a half, which is a quarter again. These are all a quarter, aren't they? So what are the only options where there's 1 heads? Well, it's just a half. So does this equal a half? Well, let's use our definition that we just plugged in up here. So it's going to be n, which is 2, choose x, which is 1, times by probability of success, which is 0.5, to the power of x, which is 1, times by 1 minus the probability of success, times the number of failures, 2 minus 1. Well, again, I'm going to have 2 choose 1 times by 0.5 to the 1 times by 0.5 to the 1. 2 choose 1. How many ways are there of choosing one object from 2 things? That's just 2. And then 0.5 times this 0.5 is a quarter. So this is a quarter. 2 times a quarter is a half. Okay, and that does agree with our gut intuition of flipping 2 coins. Now, because this is a discrete random variable, the whole idea of coding, like we were talking about up here, still applies. If you're going to perform a linear transformation, right, that's really important. So if you're going to do a linear transformation, i.e. y equals ax plus b, that's fine. When you start doing y equals ax squared plus bx plus c, that's no longer linear, and these rules don't work anymore. You've got to take it case by case. Okay, so binomial distribution, those are the key bits. A lot of it you just write it down and you figure out what's going on. Now, a note of calculator use. In your calculator, if you've got the Casio FX991EX, so if you've got the Casio FX991EX, I believe, then I believe you press menu and then option 7 for distributions. And then you will have various lists of stuff to choose from, and the binomial PD is used for when you want to find the probability that x equals to an x, And the binomial CD, the cumulative distribution, is when you want to find x being less than or equal to an x. For the Casio FXCG50, I believe you press menu, then you press 2 for statistics. F2. F2, no, not F2, just 2. Or you can just navigate to the right and press the execute button. Then you press F5 for distribution. And then you'll press F5 again, and that option should be the binomial. And then you'll get a choice of the binomial PD, which is the same as the probability of x equaling to little x, the binomial CD, which is the probability that x is less than or equal to x, and as an added bonus you will get the inverse binomial, which is really interesting because given a particular probability percentage, that will find an x value for you, so it does the reverse. And that's really useful when we talk about next week hypothesis testing and finding critical values and stuff. I mean, it's not necessarily useful for now, but that's one of the few advantages I feel the Casio FX CG50 has over the Casio 991 EX series, is that it has inbuilt inverse distribution operators inside. But it doesn't particularly matter. I mean, I'll talk how you do it with and without. But if you're wondering where I get all my numerical answers from, it's because I'm using a calculator and I'm going to be doing this thing. If you didn't have one of those calculators and you wanted to do it from scratch, then you'd have to use these formulas and play around with it like I've done over here and over here in the green bits. Okay, I mean, it's just saving you time. But I'll talk about where it all comes from. So same deal again. If you want to read the question, okay, give yourself a good 15 or so minutes. It's quite a meaty question. If you've got the calculator, it should be quicker, but it's still meaty. Okay. Plastic clothes pegs are made in various colours. The number of red pegs may be modelled by a binomial distribution with parameter p equal to 0.2. Right, so the probability of it being a red peg is 0.2. This is for reds. The contents of packets of 50 pegs of mixed colours may be considered to be random samples. Okay, so what have I got here? I've got a distribution which is distributed binomially by n is 50 and probability of success is 0.2. Getting the distribution down in your head is super duper critical. Okay, determine the probability that a pack contains less than or equal to 15 red pegs. So what's the probability that x is less than or equal to 15? So I will just use my binomial cumulative distribution. My lower bound is going to be 0 because it starts at 0. My upper bound, it goes up to 15, or just put x is 15 on the Casio FX991EX. The num trials, or the n's, well, there's 50, and the probability p is 0.2. And if you've done this right, you should get a value of 0.969 to 3 decimal places. That is a 96.9% chance of it happening. Seems legit. Now, probability exactly 10 red pegs. Okay, so the probability that x exactly equals to 10, which is going to be 50 choose 10 of probability of p, which is 0.2 to the power of 10, times by 1 minus p, which is 0.8 to the power of n minus 10, which is 40. Or, alternatively, I could go back and use my binomial PD function. So the value of x would have been 10. Yeah. Okay, so then that apparently is 0.1398 to 4 decimal places. If you put 0.140 and round it to 3, that's perfectly acceptable as well. But yeah, let me just check I did the other answer correctly because it logged in a... No, yeah. No, yeah, fine. Okay, more than 5 but fewer than 15. Okay, interesting. So the probability x is greater than 5. So greater than 5 but fewer than 15. Okay, so essentially we want to do the probability that x is less than or equal to 15, but we have to subtract the probability that x is less than or equal to 5, because then that will give us the probability that x is trapped between 6 and 15, if you think about it. I mean, if I draw a little sketch, here's the numbers 0, 1, 2, 3, 4, 5, 6, up to 15. I want the numbers from 15 to 6, don't I? So if I do from 15 to 0, I then have to subtract from 5 to 0 to get the green stuff left over. So less than or equal to 15 red pegs, I already know what that is. That's 0.969, 3 decimal places. Now I have to find the probability that x is less than or equal to 5. So binomial CD, upper limit is 5, 50, 0.2. Yep, so that is going to be 0.0480. So then if I go back to here, I want 0.969 minus 0.048. So that probability is 0.921. So about 92.1% of the time, I'm going to have more than 5 but fewer than 15 red pegs. Okay, Sly, a student, claims to have counted the number of red pegs in each of 100 packets of 50 pegs. From his result, the following values are calculated. The mean number of red pegs per packet is 10.5, and the variance of number of red pegs per packet is 20.41. Comment on the validity of Sly's claim. Okay, so we've actually got, I think, a bit of a distribution within a distribution here. Okay, so what can we do here? Do we have enough information so far? Yeah. Okay. So, first of all, what is the mean from our previous thing? Well, our expectation of x would have been just n times p, which is 50 times by 0.2. 50 times by 0.2 is 10. 10's pretty close to 20.5. Seems legit. And what would the variance be? Well, the variance would be n times p times q. So 50 times 0.2 times 1 minus 0.2, which is 0.8. So if I take that answer and times by 0.8, I get 8. Now, Sly is saying the variance of the number of red pegs per packet is 20.41. So I would argue, although the mean seems pretty close, the variance is more than double. So I would say it's not a valid claim. Okay. It shouldn't be the case that if we extend this up to 100 packets, yeah, the variance shouldn't change by that much. Well, it should be the same, it's preserved. So per packet, something's not quite right here. Yeah, that's what I'd say for that. So, yeah. Okay. Let's have a look at the next one. Each weekday, Monday to Friday, Trina catches a train from our local station. Oh, hold on. We'll pause the video, give it a go yourself, but I'm just going to go through it now. Trina catches a train from our local train station. She claims that the probability the train arrives on time at the station is 0.4 and the train's arrival time is independent of day to day. From day to day. Assuming her claims to be true, determine the probability the train arrives on time at the station on at most 3 days during a 2-week period. Okay, so for the first one, we're going to have a distribution that's binomially distributed with n being 10 and the probability of success being 0.4, and I want the probability that x on at most 3 days. So that's probability of x is less than or equal to 3. So menu, statistics, distribution, binomial, cumulative distribution. Lower bound is 0, upper bound is 3, the num trials is 10, and the probability p is 0.4. So I get that probability is 0.3823 to 4 decimal places. So about 38.23% chance of happening. Hold on, let me just read that properly. The probability the train arrives on time is that. Assuming the claims to be true, determine the probability the train arrives on time at the station on at most 3 days. Okay, so the probability it's 3 days or less is only 38%. Okay, on more than 10 days but fewer than 20 days during an 8-week period. Okay, if a 2-week period is 10, then an 8-week period is clearly 40. So now we've got a different distribution where, let's not call it B, let's call it Y is binomially distributed with N is 40, and the probability should stay the same, that's 0.4. So more than 10 days, so I want the probability that it's more than 10, but fewer than 20. Okay, so it looks like I want to do the probability of y being less than or equal to 19 minus the probability that y is less than or equal to 10. Okay, because I can't include the 10. So we've got binomial, we want 19, and number of trials is now 40, and that's okay. So this one is going to be 0.8702 minus, and if we go back, I want this to be 10, and this will be 0.0352. So that will mean I have 0.8702 minus 0.0352, which means that is an 83.5% chance of happening, or 0.835. Okay, so the probability the train arrives on time on more than 10 days but fewer than 20 is around 83.5% likely. So yeah, actually, yeah, it's not a particularly good train, is it? Okay, assuming Trina's claims to be true, determine the mean and standard deviation for the number of trains during a week then the train arrives on time at the station. Okay, so during a week, we've now got a binomial distribution where n is 5 and p is 0.4. So that means the mean, which I'll call mu, well, it doesn't particularly matter, let's call it the expectation. The expectation, the mean, is just n times p, so 5 times 0.4 I believe is just 2. And the variance is going to be that times by 0.6, which is 1.2, which means the standard deviation which we'll call sigma, lowercase sigma, is just the square root of 1.2. So that is 1.095, so it's 1.10. So what does that say? That's saying on average the train is only on time 2 out of 5 days, and most of the time it's going to be give or take 1.1 days. So sometimes it will be 0.9 days out of a week on time, and other days it will be 3.1. It's between 1, 2 and 3 really, most of the time. Each week for a period of 13 weeks, Trina's travel colleague Susie records the number of times the train arrives on time at the station. Susie's results are blah 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 blah. Calculate the mean and standard deviation of these results. Okay, the mean is just going to be the sum of all those values over how many there are. So that's quite easy. That's going to be 2 plus 2 plus 4 plus 1 plus 2 plus 3 plus 3 plus 2 plus 2 plus 0 plus 3 plus 2 plus 0. I make that 26 over 13. So for Trina, her average is 2. That's looking good because that agrees with the binomial distribution that Trina's saying. So Susie's mean is the same as our mean. Right, now let's work out the standard deviation then. So the standard deviation, the standard deviation is going to be the square root of the sum of x squareds over n minus the sum of x over n all squared. Well, over n, we know that's 13, minus, well, we know what the mean is, that's 2 squared. Now I just have to do each of these things squared. So 2 squared is 4, plus 2 squared is 4, plus 4 squared is 16, plus 1 squared is 1, plus 2 squared is 4, plus 3 squared is 9, and another 9, and a 4, and a 4, and a 0, and a 9, and a 4. So that's 68. So I need to do the square root, oh dear, the square root of fraction 68 over 13 minus 2 squared, which is minus 4. Right, okay, my calculator just did a thing. 68 over 13 minus 2 squared, which is 4. I get that, and that apparently is 1.109, which is 1.1. Hence, comment on the likely validity of Trina's claims. Well, from the observed evidence from Trina's friend Susie, she has got a mean of 2 and a standard deviation of 1.1, and by 1.11. And by modelling this as a binomial, then yeah, the expectations agree, 2 and 2, and the standard deviations agree, more or less, 1.10 to 1.11. So actually, yeah, Susie's records do back up Trina's claim, and that this does appear to be binomially distributed. Yeah. So that's it, that's the last one. Hopefully you guys understood that, and yeah, I've uploaded a load of work. Peace out.